From the protein localization sites, datasets appear to be a valuable resource for predicting the cellular localization sites of proteins based on various attributes. Here is a breakdown of the dataset and potential data limitations and quality issues. 1. Explanation of the dataset. The dataset comprises 1,484 instances for the yeast dataset. It includes 9 attributes, where 8 are predictive and 1 is a name attribute. Attributes such as MCG, GVH, ALM, MIT, ERL, POX, BAC, and NUC. It represents score or present indicator of various biochemical features related to the protein localization. 2. Data limitations and quality issues. Data completeness. One important aspect of data quality is completeness. It is essential to ensure that all instances and attributes are populated with relevant data. Since there are no missing attribute values mentioned, it seems the dataset is complete in this regard. The data consistency. Consistency ensures that data is uniform and follow a specific format. For instance, ensuring that all attribute values are in expected range or format. It is important to check for inconsistency across attributes to maintain data quality. Without explicit mention of consistency checks, it's assumed that the creators may have verified that aspect during dataset preparation. The data accuracy. Accuracy refers to the correctness of the data in this context. It would involve ensuring that the attribute values accurately represent the features they are intended to measure. The accuracy of the attribute values might have been assessed through cross-validation or comparison with no results from experiment data. Data representativeness. The dataset representativeness is crucial for generalizing predictive models to real-world scenarios. It's essential to ensure that the dataset covers a diverse range of protein localization sites, and instead to avoid bias in model predictions. The representativeness of the dataset might have been assessed by ensuring a balanced class distribution, or by including instances with various source. Temporal validities. As the dataset was created in 1996, there might be concerns about its relevance to current research. Protein localization prediction methods and understanding may have evolved since then, potentially impacting the dataset applicationally to contemporary research questions. 3. Handling data quality issues. First, preprocessing. Data preprocessing techniques such as normalization, standardization, or feature scaling may have been applied to address inconsistencies in attribute scales or format. Next is cross-validation, to assess the accuracy and generalizability of predictive models built on the dataset. Cross-validation techniques may have been employed. This involves splitting the dataset into training and testing sets multiple times to evaluate model performance on different subsets of the data. Next is feature selection. The feature selection method may have been used to identify the most relevant attributes for predicting protein localization sites, thereby mitigating the impact of irrelevant or reductant attributes on model performance. Next is regularization. Techniques like regularization may have been applied to prevent overfitting and improve model generalization to unseen data. And the last one is external validation. Results obtained of models trained on these datasets may have been compared with experimental data or predictions from other independent datasets to validate the accuracy and robustness of the model. Overall, while the dataset appears to be comprehensive and well-documented, ensuring data quality and addressing potential limitations is critical for building reliable predictive models for protein localization. Next is univariate analysis involves examining the distribution and characteristics of individual variables in the dataset. Let's perform univariate analysis on each attribute in the protein localization sites dataset. 1. Sequence name. Sequence name is an attribute likely serve as an identifier for each protein instance in the dataset. Tool analysis may involve checking for uniqueness, format, consistency, and potential correlation with the target variable or localization site. 2. MCG or McCoach method. McCoach method is for signal sequence recognition. The important information is 1. Distribution. Is for checking the distribution of score across instance. Range to identify the minimum and maximum values to understand the scale of the scores. Outliers to detect any extreme values that may require further investigation. 3. GBH or Von-Higgins method. Von-Higgins method is for signal sequence recognition. The important information is 1. Distribution. Is for examine the distribution of scores and their variability. Second is comparison, to compare the with McCoach method to understand the correlations or differences. 4. ALM or Around Membrane Spanning Region Score. The score of the Around Membrane Spanning Region prediction program. The important information is 1. Distribution. Is for checking the skewness and variability in scores. Second is interpretation. Is for understand how scores relate to the prediction of membrane spanning regions. 5. MIT or mitochondrial score. The score of discriminant analysis of the amino acid content of the N-terminal region. The important information is 1. Distribution. Is for examine the distribution of scores for mitochondrial localization prediction. Second is thresholds, to identify score thresholds for distinguishing mitochondrial and non-mitochondrial proteins. 6. ERL or presence of HDEL substring. Presence of HDEL substring is thought to act as a signal for retention in the endoplasmic reticulum domain. The important information is 1. Frequency. Is to determine the prevalence of the HDEL substring among proteins. And associations is for explore how the presence of HDEL correlates with other attributes or localization sites. 7 is POX or paroxysmal targeting signal. Paroxysmal targeting signal in the C-terminus. The important version is 1. Frequency. Frequency is for access the frequency of paroxysmal targeting signals among proteins. Second is specificity. Is for investigate how reliably the presence of the signal predicts paroxysmal localization. 8. VAC or vacuolar score. Score of the discriminant analysis of the amino acid content of vacuolar and extracellular proteins. The important information is 1. Distribution. Is to examine the distribution of scores for vacuolar prediction. Second is discrimination. Is to understand how well the score distinguishes vacuolar and extracellular proteins. And the last one, number 9, is NUC or nuclear score. Nuclear score is score of discriminant analysis of nuclear localization signals. The important information is 1. Distribution. Is for examine the distribution of scores for nuclear localization prediction. And second is thresholds, to identify score thresholds for distinguishing nuclear and non-nuclear proteins. And from conducting univariate analysis on each attribute, we can gain insight into their distributions, variability, and potential predictive power for protein localizations. And from this analysis will help in understanding the characteristics of individual attributes and their relevance to the overall prediction task. Here is a summary of the steps performed for multivariate analysis and building a predictive model. Number 1. Data preparation. We need to load the data set that containing information on protein localization sites, then check for missing values and convert categorical variables into numerical format. Number 2. Multivariate analysis. We will calculate the correlation matrix between features and visualize the correlation matrix using a heat map to understand the relationships between variables. Number 3. Model building. We need to split the dataset into training and testing sets, then utilize the random forest classifier algorithm for classification, and train the model on the training set. And last one, model evaluation. We will predict on the testing set using the trained model. Then calculate the accuracy of the model and generate a classification report showing precision, recall, F1 score, and support for each class. And the random forest classifier model can be further optimized and evaluated based on the result obtained. If you have any future questions or need additional assistance, feel free to ask.
Import library and load data set. The code starts by importing the necessary library for data manipulation and plotting, such as pandas, numpy, matplotlib, and seaborn. Then it loads the data set using pandas.read_csv parentheses and define a column name using the name parameter. It uses the .head parentheses method to display the first few rows of the data frame to check if the data is loaded correctly. Track 1. Data interpolation quality issue. It checks for matching data using ignore parentheses.sum parentheses to see the number of matching values in a column. It uses .info parentheses to check the data type and total number of data. It uses .describe parentheses to view basic statistics of numerical data. Check for unique value in the class column using .unique parentheses plot the class. Attribution using count plot parentheses Track 2. Universal analysis. Plot histogram chart for all numerical variables using .hint parentheses plot a box plot for the MCG variable for visualize for data distribution. Track 3. Multivariate analysis and predictive model create a correlation matrix to see the relationship between variables using heat map parentheses split the data info feature and target variable. Split the data into training and tracing set using train_test_spin parentheses Build a predictive model using random forest classifier. Evaluate the model by calculating accuracy and classification report using accuracy_score parentheses and classification_report parentheses